I'm going to try to finish at least the PCA part before lunch, and then if it's still running, it still runs. At least it finished for me, which is the important thing. Um, so we were at that state where we transform our counts. We apply one transformation or the other. I don't know which one did you guys apply. Um, so basically, we got a new object with our count data, but it's been transformed. So again, we have samples in the columns, genes in the rows, but this is the transformed data now. I'm going to insist this transformed data is not used for analysis. We already done the analysis when those two lines, when we call these seq2. So these data, we're going to use it for plotting, like PCAs, heat maps, and things like that. So the next step is principal component analysis, and is when we're going to use the transformed data. And I was saying that we can use the principal component analysis function that seq2 provides. And basically it takes the new object that we created, and also it's going to request, if you want to, how many genes do you want to use for this. It's going to be stored based on the variability of the genes. The highest variable genes are going to be in top. And you can take, for example, the top 5,000 genes if you want to. The idea is the most variable genes are going to be the ones with the most information. Probably it's not going to change if I say 10,000, because I'm already reaching the most variable genes, the one that has more information. You can try. We can change numbers to see how much the PCA changes.
I think it was slow because people have executed the command multiple times.
Could be. I'm not sure. Well, if it's multiple times, it's going to go back and restart. It's going to go back and restart. It's going to be a restart.
So when I'm checking my kernel status, it is showing as busy, and it is showing executed 8 out of 17 cells.
It says, sorry, 8?
8 upon 17 cells. What does that mean?
Oh, no, that could be the total steps that we have, the total cells that you need to execute, and you have executed 8. No? I don't think so. Or maybe, I don't know. I'm not sure.
You may say 4 out of 6 cells are executed.
Oof. You cannot read it, but I need to do this to be able to show the plot, right? So you're going to get a plot similar to this. Do we have a good clustering based on our condition? It seems so, right? We PC1. So if you could, you can do a plot only using one principal component, right? I mean, it will look like a line and dots on top of a line. But at the end, I mean, PC2 is not telling us much about the story here. It's just PC1 who is splitting normal on the left and sleep deprived on the right. But if you could, you do one PC plot, and all dots would accumulate in one side and the others in the other side. So yes, we have good grouping. The ones in the back or the ones in the front row probably don't see it, but you have it in front of the screen. You also can see how much of the variance PC1 is explaining and how much of the variance PC2 is explaining. So PC1 is having a good separation, but only explaining 37% of the variability in the data. So we could say that, we can phrase it differently, right? We could say that our condition, being sleep deprived, is only explaining 37% of the data, right? Or the variability in the data. So we have 67.3% that is explained by other reasons. It could be technical. It could be, again, we also have a knockout. It could be the knockout, right? We keep track of the mice that were knocked out. It could be that knockout is explaining some of the variability of the data. And again, hidden factors that we are not aware of.
If we change the condition, like we have changed it for the genotype, so we are getting a PC plot like a scattered plot. Right now we have done the comparison between the condition.
Yeah, again, here we are not doing any comparison. So we are grouping the samples or coloring the samples based on the metadata. That's it. So we provide them exactly the same data. In this case, the next cell. What we're doing in the next cell is basically the PRCOM is the principal component function, the native R function, the one that is included in the basic R, to do principal components. So here, I'm just repeating the previous step using the native function of R. Basically, it returns a new object, and instead of keeping the whole object, what I'm doing is just getting the data points for creating the PCI plot. I store it in here. I'm giving names for the rows, which are our samples, giving names for our columns. So what we're getting here at the end is a new matrix of all the principal components. The coordinates, sorry. The coordinates to be able to plot a new PCA. Oh, and it's going to take forever? No. OK, so basically what I'm doing here is I'd obtain all our PCs and our all samples and the coordinates. So now I can take this and use any plotting system and replotting the PCA. Why I'm doing all this transformation is because how the data is returning as an object. But don't worry about it. I mean, I'm just showing you can just plot the PCA using the normal function. I like to retrieve this data because it gives me, or calculate it using the base function, because I'm able to plot more things easily or modify the plots as I want. And we will see how we're going to do it next. For now, the only thing you need to know is we have this giant matrix or data frame with the coordinates to plot PC1, 2, 3, 4, and 5, and for every sample. What is PC? PC is the principal component number 1. PC is principal component number 2. When you do a PCA analysis, I explained that yesterday, what you're doing is reducing the dimensions of your data. Your data has, I think in this case, we reduce it to 15,000 genes. So you have 15, no, in this case, we're using all, oh, by the way, in here, I'm not selecting genes. I'm using the whole data set. In the previous step, I chose the top 5,000 genes to the PCA. Here, I'm choosing everything. So it could be slight differences between this and the previous PCA. So a principal component, so going ahead. So the PCA, what you're doing is reducing the dimensions of your data to a new axis or new dimensions, which are completely independent of each other. So this is a new dimension. A PC, a principal component, is a set of genes with different weights. And that, we need to do statistics to explain how all the steps go. But this is a new dimension of your data. You've been reducing to these new dimensions. And each principal component explains the proportion of your data, of the variability in your data. That's what a PC is. So in the previous plot, we're explaining, we're plotting PC1 and PC2. But there are other principal components. I don't even know how to speak now. So another thing that I can do, you remember we talked about the percentage of variability the data explains. When we created, or when we use the PRCOM function and it created a PCI object, it stores everything, the principal components and the importance of each one of them. So to be able to access that, I need to use all these complicated things. It's not that complicated. Basically, I'm access the summary of that object, and there is, let's say, one column or one part of that object that contains all the importance, in this case they call it, or how much variability of the data, each principal component, 1, 2, 3, 4, and so on, it explains. And I'm storing them in a variable. So each variable here is just containing a percentage. That's it. Something that we haven't taught here is how to plot with ggplot. So you don't know all these functions, right? So don't worry about it. But ggplot is a library for plotting. It's really powerful, better than the basic R, and it allows you to do really cool plots. And oh, well, we did one, right? I think the first day. Yeah, we used it the first day.
Francis, there's other thing. So the second Word file that we did not open yesterday is about ggplot, and it has like all the detailed instructions like how you plot a ggplot. Just run the code, you will actually make sense out of it.
So basically, I'm giving our metrics. I'm asking plot PC1 and plot PC2, and then modify that plot with other things, right? Let's annotate every sample. give the label for x-axis and y-axis, and use the percentage of variability explained added also to those labels, right? And they come with different themes, so you can play with the colors and all that. So if I do it, I store the plot on a new variable, and then I print it. Or I show it on the screen. Sorry, I missed one step, right? Sorry, I didn't run this. It's definitely nicer than the previous one. So now we have all the labels, all the samples being labeled, and pretty much it's telling us the same story, right? That it's separating normal and sleep deprived, and we also printed the percentage of variability explained for each principal component. It is slightly different, right? I think it was 37 in the first one. Now we got 34, still in the same range. So clearly, our condition and the study is not explaining everything. But enough at least to separate. Well, okay, one thing we can say for sure is the main source of variability in our data, right, is it's been sleep deprived or not. That we know. Okay, can you plot PC3 and 4? Let's plot it. Actually, this command, this ggplot could be shorter. Now that I realize. Any problems plotting PC3 and 4? Everything good? I shortened the code, so if it looks different from the one that you did it, is because actually there were extra information that is not needed for ggplot to plot it. Thank you. I guess you could. Okay, good. Yep.
We have plotted for PC3, PC4. So the variability is 9.5 versus 6.5.
90? No.
We have plotted for PC3 versus PC4.
It cannot be 90.
It is 9.5.
Oh, 9, yes. 90, no. Okay. Yep.
Right? So PC1 versus PC2.
Oh, sorry, I did a mistake.
It
My
was
bad.
almost similar, so we have to place it.
My bad.
9.5.
Yeah, yep. I made a mistake. Thank you. I think Bonnie already showed you how to do a bar plot. So if we want to access of the percentage of how much the percentage of the variability is explained by every PC, we can access through the same way we did before with summary, PCA, importance. This is a section that is proportion of variance. Here I'm just multiplying by 100, so we get a percentage instead of a fraction. That's the only thing. Yes, I mean, by default, if you do principal component analysis, they are always sorted. So, and the first two are the ones that explain the most.
So it is two, it is even odd number which is coming in. 2 is not here, 4 is not here.
Oh, that's just the labels.
Okay.
But the second column, it's 2.
There, it's there.
It's there, yes.
Column.
Well, before that, I mean, PC3, PC4 is not telling us much because we don't have much information. The only we have is we know that it's a sleep deprived or not, nothing else. So it's difficult to come out with something here. There's no specific separation of anything.
So this PCA plot will always be on 1 and 2.
Sorry, what?
PCA plot will always be on 1 and 2 because
Oh, well, it's the first one you're going to look at it. But you can look at more PCs if you want to. I don't have a good example, real data, why you can go 3 and 4, but the example that I did yesterday, the separation by treatment was PC3. So if you don't plot it, you're not going to see that separation. So, but what we know, right, is PC1 is separating a sleep deprived and not. So we know that the main source of variability is that, is being a sleep deprived or not. The other sources, we don't know.
Distribution of genes is distributed over the dimensions. So it depends upon your data. Again,
variation in the data.
yes.
I mean, I'm trying to explain what the PCA tell us. That's it. It's me putting an explanation on it. The principal component analysis doesn't know anything, right? It just knows every sample, and it's doing a principal component analysis based on the variability in your samples. That's it.
So wait, that's what I'm talking.
Yep.
So we have variability in our samples. So
Yep.
we are getting the data between the samples. So
Yep.
PCA plots is just the description of the variation in our data.
Correct. In a way that you can read it, going from 20,000 to only 2 dimensions. Yeah.
But my point is, so it is distributed upon PC1 versus PC2, PC3 versus PC4.
Yes, because they're totaling that part of the principal component analysis tells you that every principal component is completely independent. It's orthogonally independent from the next one. That's why you have it completely divided.
No, dependent.
There's no overlap.
Independent.
It's a dependent, sorry, independent. I meant that.
No, suppose you have 20,000 genes. So my understanding, what I
Yep.
understand about PCA plot is, suppose you have 20,000 genes in your data.
Yes.
Yeah, for 10 samples,
Yep.
distributed over the 10, 5 in the treated or
Yes.
non-treated groups. So we have 2 groups, right?
Yes, but the groups doesn't play any role in principal component analysis. Yeah, okay. To be clear.
I'm giving the example.
Yeah.
So we have 2 groups, treated and treated,
Yeah.
and we have 20,000 genes.
Yes.
The variation is quite much in those samples
Yes.
or groups. So PC1 versus PC2 is suppose is the data of approximately 16,000 genes, and PC3 versus PC4 has data of 2,000 genes.
No. They can have all of them. So a principal component can be all genes, but they are weighted differently.
Why? So why they?
Well, then we can go into statistics, which I'm not an expert, right? But that's the main idea. It's a linear combination of all the genes, and every gene is weighted differently. So genes that don't variate, they have a weight of 0, meaning they don't contribute to the principal components.
Okay.
Genes that have high variability, again, I'm not an expert. I remember doing it by hand when it was an undergrad, right? I remember doing principal components by hand just to learn how is it, but I don't even remember the details. So I'm not going to be able to explain you the details.
Variation in the gene expression. Suppose PC1 is telling us 50% of the variation or 60% of the variation is spread over the PC1. PC1 plot is telling me the maximum percentage of the variation in the data, not in the sample.
So should we stop here? Yep, okay. Any questions about principal components? How we plot them? I gave you two options. If you like ggplot and you want to learn, use Bonnie's notebook to practice, or ChatGPT. Don't use my example because I also make mistakes, right? So I know this section here, you can skip it totally. You don't need it. I tell you the truth, I use ChatGPT a lot for ggplots because I'm not able to remember all the parameters. I don't remember them. Okay, let's break then and be back at 2, the latest.